Now this represents the Earth with geostationary satellites going around. Now you'll notice that each satellite stays vertically above certain points on the equator. That's why they're called geostationary satellites. Now we want to find a relationship between the speed of the satellites and the distance from the center of the Earth. Now this represents a typical orbit for a satellite, and we need to notice that the center of the orbit is the center of the Earth. Now I'm going to change it slightly. Now you'll notice that the center of the orbit is still the center of the Earth, so satellites can rotate around the Earth at this sort of angle. However, if I change it like this, you'll see that the center of the orbit is not the center of the Earth, and we can't actually have satellites circling the Earth like this. Now let's consider this satellite going around the Earth. The radius of the Earth is this number, and let the mass of the Earth be capital M and the mass of the satellite be small m. Now the distance of the satellite from the center of the Earth is r, and the universal constant of gravitation is capital G. Now we need to use a little bit of physics here. For a mass m at the surface of the Earth, we talk about its weight is mg, where g is the acceleration due to gravity. But if we're thinking of gravitation, the force between the mass and the mass of the Earth is proportional to the product of the masses and inversely proportional to the distance between them. And the distance between them, if it's on the surface of the Earth, is the radius of the Earth. And this is r squared on the bottom. And putting this universal constant of gravitation, we can equate these two things. Now, cancelling out the m, small m, we get gr squared is capital G m. Now, the force required to keep the satellite in circular orbit is mv squared over r. And this must be provided by the gravitational force of gmm over r squared between the Earth and the satellite. Therefore, putting these equal, putting this equal to this, cancelling out the m's and multiplying by r squared, we get rv squared equals gm, but gm equals gr squared. So we change that to gr squared. And then if we work this out, it comes very close to just 4 times 10 to the 14, which is a constant number. R times v squared is a constant number. Now let's consider what this actually means. If v increases, then r must decrease, because this product has to be a constant number. So if v increases and r decreases, the satellite circles closer to the Earth. If v decreases, then r must increase, so the product becomes the same number. And if r increases, the satellite circles further from the Earth, further away. Now look at some particular numbers, simple numbers. If the velocity is 2,000 meters per second, the calculation is here for the distance to the center of the Earth, and it's about 94,000 kilometers. But if the velocity is 4,000 meters per second, the distance to the center of the Earth is only about 19,000 kilometers. Now we're particularly interested in the geostationary satellites, So if the satellite takes 24 hours to circle the Earth, it travels a total distance of 2 pi r in 24 hours. The Earth also takes 24 hours to rotate, so the satellite appears to be stationary above a particular place on the equator. Therefore, the satellite's velocity is 2 pi r over 24, and if we work this out in meters per second, it comes to this. And substituting this value of v into rv squared equals 4 times 10 to the 14, we get this equals 4 times 10 to the 14. Then we get an r cubed in here, and finally r cubed equals this number here. Now this so happens that the distance of the satellite is about 42,200 kilometers from the center of the Earth. Subtracting the radius of the Earth, we get the distance of the satellite from the surface of the Earth at the equator, which is 35,800 kilometers approximately. This is about 6 times the radius of the Earth above the equator. And the value of v is about 3,000 meters per second, which is approximately 11,000 kilometers an hour. Now this represents the Earth, and we're directly above the North Pole out in space looking down. This is a point on the equator, and this is a satellite fairly close in. This is a satellite a bit further out, and this is much further out. Now the velocity of the one further in is going to be moving quickly, and the one further out is moving more slowly, and this one is actually going to be the geostationary satellite. Now let's see how they move. Now in 6 hours, the Earth will have rotated 90 degrees. And you'll notice that this geostationary satellite is still directly above the same point on the Earth. Now in 24 hours, it'll be back round here again, so we'll carry on with the motion. This is 12 hours. 18 hours. 'And that's the full day. 24 hours.